Go. All right, so now we're recording. Okay, so graphs. All right, so let's look at a linked list again. So if we come in here, a linked list, again, you think of it as kind of like this chain. You have a value, and then you have a property on it that points to the next item. So it's kind of this like single chain. So a tree, well, let's see. You know what? We're going to switch the order of this. We're going to start with a tree before we go into graphs, just because a graph seems to build off of a tree a little bit better. So, all right. So a linked list, it's just this. You have this node, it points to the next one. This node points to the next one. This node points to the next one. So you have them all in sequence. And then what you do is, so the difference between a linked list and a tree is that a tree data structure essentially has, this is a good little diagram of it, a tree data structure. And this one just happens to have two, but a tree can have, by default can have as many different, children, coming off of it as, as you'd like. So,
am I supposed to be seeing a picture?
Oh, am I not screen sharing? Not yet. Okay, sorry about that, guys. The recording, you'll see it. The recording, you will see my screen. Okay, all right. There we go. Okay, thanks for the reminder there. Okay, so anyway, if we come back in here and look at, we look at this linked list. You see we have these different nodes. They just connect one to the next. They only connect to one. They only have one other node that they connect to. A tree is where this node could connect to like 5 nodes. And then those nodes could all connect to 5 nodes. And those nodes could connect to more nodes. So the way to kind of visualize it is to think of like your family tree. Like there's you, and then you have your, you have your grandparents, or like your parents, and they have their grandparents, your great-grandparents, etc. That's exactly what a tree is. If you were building a genealogy site, you would have a tree data structure is what you would use to structure that data. So it's so we have a tree here. Let's actually I'm going to go into this Wikipedia page. I think so. There's an unordered tree. Often they are restricted to only having 2 children. It's not necessarily required, but often they call them those binary trees. So a binary tree is where each node only has 2 children. A binary search tree is where the children maintain order. So the left node is always less. Well, this one isn't binary, but this was just a tree because the items that have no real order to them. But in a binary search tree, the items on the left would be less than that node, and the items to the right would be greater than it. And so let's walk through and look at a binary search tree diagram. All right, binary search tree, or BST, is this right here. So with 8, we have the node to the left is a 3, the node to the right is 10, so the node, and then you go to the 3, and then the node to the left of it is 1, right of it is 6, 4, 7. And so it, when you add something to it, it can be a little tricky because you have to maintain this, this order. And so what this allows for is it allows for very, very fast searching if your data can become structured as a binary search tree. Because if you want to find a value, you can just look at this first one and say, is the thing that I'm looking for, is it to the right or is it to the left? And then you can jump over, and anyway, you can get down and access your data very quickly when it's structured as a binary search tree. But Anyway, so binary search tree and binary search are two different concepts. So binary search is where you divide the array in half, and then look in the middle of the half that's remaining. We kind of talked about that a little bit. Go over that more later. But Ty, question.
So does so I know you said binary just allows two different things.
Uh-huh.
Do the parents have to be in the exact node, or can they just be
Yeah.
any
So they can be any number, but then you can also do different things to try to keep it balanced. And so, yeah, here's some of the problems and hence some of the challenges of the binary search tree, because the search tree is more effective if you can keep it balanced. Because maybe on one side, if like the middle number is 50, but then maybe so you see here there's like 1, 2, 3. It's 3 layers deep. Maybe on one side it goes 50 layers deep, and then on the other side it only goes like 2 layers deep. And so then it's totally out of whack. And so, yeah, so some challenges or some algorithms, and these are, these might come up in your coding challenges later in the course. Is let's say you're given an unbalanced binary search tree, and then you need to go in and rebalance it. So you rebalance the search tree. Or something you have to be careful of is, let's say we have 8, and then it goes to 10. And then we put a 9 right here, and then let's say we put an 8 again, and then a 7, and and you're getting your values out of order, or anyway, so it's if a duplicate, if you see that duplicate happening there, so it's generally that's not too big of a deal, because if you're going to insert a 3 or something like to the left of this or to this node, then you're going to start by going to the left of it, and so you're never going to see anything that's really like greater than 8, or you shouldn't. But those are kind of things to watch out for. So I know this is kind of I'm speaking kind of abstractly, and so I don't. It's when I start just speaking these terms, I start throwing out a lot of vocab words that perhaps make it a little difficult to understand. But anyway. Trees, some examples of trees. I posted them in here as well. You can think of a tree as like your family tree, the file and the folder structure on your computer. So like you have your root, and then you have all these folders, and you navigate down into them, and then there's other folders, and then other folders, and it's kind of like you have this tree data structure that all spreads out from a single node, a single folder. So like folders inside of folders. So that's kind of like a tree data structure. Anyway, yeah, they're very common. Trees are used quite a bit. And and so binary search and a binary search tree are different. Binary search tree is it's a tree data structure where, as you insert nodes, if they're less than the midpoint, they go to the left. If they're right of the midpoint, they go to the right. And then you repeat that. If it's so, like if we wanted to insert the value, 5 into this data structure, we would start here. We'd look at 8. And we say, is 5 less than or greater than 8? It's less than, so we go to the left. Is 5 less than or greater than 3? Greater than, so we go to the right. Is 5 less than or greater than 6? Less than, so we go to the left, but then we see it's 4, so it needs to be where 4 is. So what we would do is we would replace 4 with 5, and then 4 would now be down here, attached off of 5 in a 4th layer. So anyway, that's how the binary search tree is structured. And the important thing, again, is that just each node has a value and then a left property and a right property. This is one direction. They flow down. The nodes down here, they don't know anything about the nodes above them. It's that each node is only concerned with its value and then a left and a right property. Okay. Any thoughts on this, or any questions? Yeah. Yep. So that's that's natural. So in JavaScript terms, think of each of these circles as a JavaScript object. So each one of these is like an object, and then there's there's a value on here which is the number, and then there's a left and a right property. So it's kind of like your linked list, except for instead of just pointing exactly. Instead of just previous or next, you have left and right. So that's one way that you can structure this. If you're just doing a tree with an infinite number of potential children beneath it, then you could do an array. So each node would have an array property of children that you would just push and add on to. Okay. All right, so binary search tree. Okay. Have I gone over binary search with you guys? By giving you like the... Okay. All right. We'll be going over binary search with arrays. That'll be one of your coding challenges later in the course. But yeah, again, I just want to make sure that you're not mixing these two up, so you're not like, when you see the binary search problem, you're like, oh, I need to create this tree data structure. But that's, yeah. All right. So, all right. So linked list is kind of like, just, from 1 to 1 to 1. A tree is if it's connecting to many different spots. A binary search tree is the node is connecting to 2 spots, and then those spots have to be, either less than or greater than. Yeah, Ty?
The other question I had is, what is the big O notation for searching a binary search tree? I probably realize it's not important right now, but it would just help me connect to.
Yeah.
It says it right there.
Yep. So search is O log n, and then worst case. So there's the average case and the worst case. So these are different ways that you look at it, but worst case is linear. So worst case is linear to search through a binary search tree. But then, yeah, average is this. I think the reason it's worst case like that is because just with balancing or being at, it could be potentially be really out of whack and really weird. So. Yeah, so yeah, when you search these data structures and these algorithms and stuff like that, a lot of those details will be on here on Wikipedia, so it's a pretty good reference. So kind of crazy enough, this was invented in 1960, so long time ago. All right, so now the next data structure. Oh, not JS. You can do that. You can search these data structures and look for examples of them implemented in JavaScript. And that could be helpful. So a graph is where you have an I don't want to look at that. That's a data type I want. Okay, here we go. Here's a good example of a graph. So in a graph, you have, it's just, there's no like you can have like entry points, or you can have specific nodes that you want to reference, you want to start at, but the it's not like a linked list where it's all going in a single order. And so like one common like challenge or question that comes up with linked lists, and this is something that I'll be giving you questions about, is how do you prevent circular like loops inside of a linked list, because you can sometimes get it where your linked list can have like a circle. It can like close in on itself, and then you'll get into this like infinite loop as you try to traverse it. And so anyway, that with a graph, it's interesting because the nodes that you add, it can be connected to all these other nodes, and then these nodes can be connected to any other nodes, and the connections go both ways. So you can have them go one way, or you can have them go two ways. So right here, A, if we're saying this is a two-way connection, A is connected to C, but C is also looking back and connected to A. Whereas if you looked at the binary search tree, it's only a one-way connection down. Same with a linked list. A linked list only has that one-way connection. So this 8 node knows about 3 and it knows about 10, but 3 doesn't know about 8 and 10 doesn't know about 8 either. So they kind of see down like that. Whereas in a graph, A can see C can see A can see B can see A can see D can see A, D can see E. They can see back and forth, and so it's much less. There's much less structure to it. It's a little more free form. But graphs are really, really cool because with them you can mimic a lot of real-world scenarios with graphs. So like here's another good example of what of a graph where you have these nodes, and you can think of these as objects. It's an object, and then it has an array of edges, and then an edge is where the graph points to another, or where the graph node points to another graph node. So this would be so in this array, these graph nodes have a singular. It's a singular connection. So A is connected to B, but B is not connected to A. But as you see, we don't care about loops, and there's much more freedom to it. Graphs are pretty cool because usually you structure them and set them up, and then you feed your data into your application, and you let them form into whatever skiwampus shape they form into, and then you can gain a lot of interesting insights from the unique structures that they form. So an example of that would be, think about like LinkedIn. So a social network, and everyone on the social network is a node. And so when you friend someone, or you add someone, like you connect with someone is a term they use, you send them a request, and then when they accept that request, then you're connected to them, and then they're connected back to you. It's a two-way connection. And so if you were to visualize yourself on LinkedIn, then you would have your little node that's you, and then all your connections, you could imagine all these arrows shooting out. So if you have like 500 connections, you can imagine these 500 arrows coming out from your node, all connecting to other people's nodes. And then those nodes could all be connected to 500 other nodes. And you have this big interconnected web and weaving of all these different nodes, and then from that you can do some really cool searching and different things like that. And you can do things like of the people that are connected to this node. So like, let's say, a school is a node, a different type of a node in the graph. So we can say all the people who went to Stanford, and we can connect them. And then we could look and see who all those people are connected to. And we could find out, oh, like a huge amount of people that went to Stanford also are, have worked here at this point. Or all the people who went to this school, they're, they generally, they're going into these types of jobs. So there's lots of interesting insights that you can gain from graphs. Social networks are all they're many of them are structured using using a graph. So you could think of like Facebook, or this one right here we have in front of us is kind of like Twitter. So A is someone, and it's like I'm following B, but B's not following me back. So it's just a one-way connection. And then B is following these two guys. This guy's following this one. This guy's following this lady. This lady's following this guy. But they're one-way connections. So a one-way or a two-way connection could be possible in this. So this is like kind of what Twitter would look like. Graphs can also be used for like location and distance. So like imagine that now these nodes are all cities on a map. And so with these different nodes and how they're connected, and these different distances, you can add weights and different properties to them. So you can say that this edge has a value, has a certain value. And so then there's different algorithms that you have that allow you to, search, and it will compare the weights of the edges, and it will take the path of least resistance, and, we'll seek out a path towards a destination. So graphs are used with mapping and, and finding point, from point A to point B. They're used in social networks. They're used for recommendation algorithms. Recommendation algorithms are often built using graph databases. Yeah, and so it's interesting. As a graph, it can be a data structure, so like living in memory. It can also be a database. They have so like Neo4j is a graph database, and so it actually saves this data like this in this form to your computer. And then there's lots of interesting insights and things you can do. So the way um, the way that something like a let me do here, let me I'm going to stop sharing real quick, and then I'm going to share a whiteboard. Okay. All right, so if we have this node, and then let's say that this represents like a restaurant, and then we have like these other like user nodes right here. So these are all user nodes, and if they like the restaurant, then we can form an edge between them and that restaurant node. And then let's say that here's 2 other restaurants, and then let's say these 4 people, or let's say, okay, and then all the people, they all like this restaurant too. And then we'll say that 4 of the people like this restaurant, but this guy's never eaten there. We can then say, based off of these connections, we can analyze the connections, and we could say, okay, there's nodes that this node is very similar to, but and they're all connected to this node over here, this restaurant node, but this node hasn't been connected to that one yet. So we can then make the recommendation of like, hey, you would like, you would like to, potentially go and try this out. This could, be really good for you, or like with music on Spotify, or products on Amazon or whatever. So graph databases can there's a lot of really cool things you can do with graph databases. Even structuring like using it to mimic like your brain, nodes inside of your brain, a little more freeform, and how they connect. And anyway, there's lots of cool stuff going on with graph databases.
What's an edge? You said something about.
Oh yeah, oh oops, that killed my screen share. All right. So an edge is a connection. So when we use the term edge in a graph, the edge is the connection from one graph node to another. And so the edge can be like, it can be like in one direction, or it can be in both directions. So we can either be connecting just A to B, like so Twitter. So like if this is like a Twitter user and I'm following B, that would be a one-way edge. But then if it's like Facebook and I have to send a request and then we both become friends, then that would be a two-way edge if this was Facebook, because then we're both connected to each other. Or like Instagram, it's like, this person's privacy policy is such that this person can just follow, but then let's say this person's privacy policy is very closed, so when this guy tries to follow him, this guy has to accept, and when they do that, they can like form a connection. Well, I guess that's a little. Well, I guess it would actually be kind of a permission connection that it would remember which ones. But anyway, so yeah, those are the basics of graphs. Graphs are really, really cool. I really like graphs. Actually, when I was in San Francisco at the boot camp that I went to, my project that I worked on with my group, we had a graph database using Neo4j, and my team, this one person, they found an open source or a huge data set of all these different kinds of beer. And so we downloaded all the beer, and then we fed it into our graph database, and then we would our application would create users, and the users would rate different beers that they liked, and then based off of the different properties and things like that, we would make recommendations to the users based off of which users with similar tastes, like what beers they liked. And so Anyway, it allows you to find similar users, and then you can easily make recommendations, to that group, because you can start to identify groups of people that have similar tastes. So anyway, so yeah, kind of cool. So graph databases, this one's pretty fun. There's a lot of different functions and methods and things that you'll have to make in this upcoming project. Okay. All right, so high level, those are the 3 data structures: tree, binary search tree, and graph. Okay. You guys have any questions about these ones?
I think I'd have to look at them first.
Yeah. Yep. So let me pull up a another tree data structure diagram again. There's another. Okay, so here's one. So here in this data structure, you see that it connects to 3 different nodes. This one connects to 3. This one connects to 1, and then 2. And it feeds down like this. Another example of this could be like the hierarchy in an organization. You could have like the top admin, or the person who's in charge, and then the people that report to that person. And anyway, that's another common way of like structuring a tree, but or another use case for a tree. But so when we're searching inside of here, there's something that's called depth first search, and then there's something called breadth first search. So depth first search is where we just start with 1 node, and then we go all the way down to the bottom, and then we go back up, and then down, and then we start here. We go down, 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 then go up, here, here, here. Okay, and I'll kind of annotate it. So, yeah. So depth first is we go here, we go here, we go here, then we go here, then here, 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 and this is generally either with like your while loop or your recursive loop. This is very easy. These are generally easier to write. The tricky one is what's called breadth first search, and so breadth first search is where you go. You search like this. You search all along this top level, and then you then you go down to here, then you go 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 to there. Then you drop down like this, and so you're going level by level, and so that's much trickier to implement. And so generally, with inside of a tree, you can just do a depth first search pretty quick, no problem. The times when you absolutely need breadth first search are when you are in drawing. Oh my goodness. All right, I guess I gotta close that. Okay. So are the times when you're inside of a graph. Because in a graph, let's say like right here, if imagine that these are all 2-way edges. If I were to start here, and let's say I wanted to find, what is the, there's a city, and I want to find, what's the, or I don't know, I'm looking for something that's close, something that's close to this node. If I do depth first search, I'm going to go here, I'm going to go here, I'm going to go here, and here, and here, and then here, and then here, and then potentially back to here if I'm not careful and I don't structure it right, and then I can get stuck in an infinite loop. So you have to be careful, and you may mark nodes as you pass, so you know that as I get back to one I've already seen, then I know that I'm that I'm done going down this path. So then I would start going down the next path. But even then, with a depth first search, you're going to go all the way down before you get all the way through. And so maybe if this is the node you want, or if you're looking for close nodes, you're going to end up searching nodes that are really far away before you can find the close ones. And so, I mean, you may just Anyway, so in a graph, generally when you're searching in a graph, it's going to be breadth first search. You want to search here, you want to search here, you want to search there. And then we'll start with this node and search those two, and then start with this node and search those two. And it's this one's trickier to implement, but we'll talk about that. You won't. There's an extra credit problem where you will implement a breadth first search, but everything else is depth first search. Okay. All right. So fun stuff. Graphs and trees. I love working on these. So it's these are pretty fun. Okay. Do you guys have any questions about this?
Not at the moment. I'm still trying to wrap my head around how breadth first would work.
Yeah. So it's a little true.
I have, let's see, what am I looking at? I have, I'm looking at this book
Uh-huh.
called Grokking.
Oh yeah. Uh-huh.
That's the one I was reading when I was trying to figure out what the hell knowledge was.
Nice. Okay,
And
great.
it's got very simple, like, little cartoon pictures.
Perfect.
Uh,
Do they leave a good example for graphs?
yeah, I'm trying to make it show notes.
Okay.
Okay, so their example is, like if you have a bunch of places on a map and you want to figure out the fastest way to get to, say, like, there's, this must be the same as that traveling salesman
Yep.
example,
Yeah. Uh-huh.
right, where he has to figure out the fastest way to hit every city that he has to hit without going through the same one twice and not crossing back and forth across the country and waste your time, I guess, right?
Mm-hmm. Cool. Yeah. So
Does that help? Ty? Or do you want to see what
If you were showing something on screen, it's not showing up.
Okay, I'm not showing it yet. I keep forgetting my hotkeys and then I can't find the little window there. There it is. Okay, share screen. Can you see that?
cool.
Yes.
Okay, so this says, suppose you're in San Francisco, you want to go from Twin Peaks to the Golden Gate Bridge. You want to get there by bus with the minimum number of transfers. Here are your options. That's what it says. So this first one says, here are all the places that you can get to in one step. And it's missing the bridge for one step. And then can you get there in 2 steps? And still the bridge, haven't reached the bridge, so 3 steps. So now it says this is the fastest way to get there. 3 buses. Yeah. That help?
Yeah. That would be useful for that, yeah.
Cool. Thanks for sharing that. That's really good. So, graphs, fun stuff. I mean, honestly, half the time when I'm wanting to learn something or get a good visual for it, I'll often just do a Google search, graph data structure example, and it's sometimes there's dumb ones, but as you go through, you start to kind of see some different examples that can help. Like here's kind of like one again, like with like the whole mapping idea. Like these would be like different nodes on the graph, and anyway, like the different connections can have different like weights associated with them, based on like difference and things like that, or distance, I mean. So Yeah, language, like language analysis, and anyway, graphs are pretty cool. I think there's lots of cool, lots of interesting things we could do with them. So, all right. Well, I will post you guys the homework. The way that I would like you guys to work on this is to do it in pair programming. So the way that will work is you guys will fork the repository, clone it down, and then and so then like one of you will work on it, and then the other one will be like watching. So it's like you're kind of watching over the shoulder, and you kind of like drive. So one of you, the person who's at the keyboard, you're the one who's driving, and so it's like sorry, just let me, yeah. So it's like, you know, you're the one that's driving the car, and then the other one who's observing is the one who is navigating. They're the one that has their phone open, the GPS, and they're figuring out where to go. So when you're coding, there's the person who is writing the code, and then the other person is kind of directing it, watching for like typos and mistakes, and but then you're both talking about what you're working on, and then, you know, both working to understand it together and you know, come up with a solution. So you know, you'll want to trade off every I don't know, 20 minutes, half an hour. I mean, you guys can set it, but just make sure that it's, you know, you're trading off doing it. And when you trade off, the person who's been writing the code will add, commit, and push. So then that way, when you swap, the next person who will be writing, they can just do, you know, get pull, and they can pull from the fork that you guys cloned from. So they can just go get pull origin master, and then they'll get down all of the stuff that you guys just had worked on. So that's how you can keep your code bases in sync. I think it'll be a good Git practice as well. And yeah, so that's what we're doing in the part-time class, is we're having all the part-time students work in pairs. And we'll, you know, try this with you guys. And, you know, just because it's the two of you, you know, we'll probably just like switch, and, you know, sometimes you'll just work on your own. Sometimes we'll have you partner together. But yeah. So have any questions about that, or any concerns?
No, I don't think so.
Nope.
Okay, great. And then when you guys jump into a video call, let me actually, I mean, I guess just it's only going to be you guys in the full-time channel, pretty much. Just like me, Austin, you guys will be the only ones in there. So what we'll do is you guys can just post your Google Hangout link in the channel. So that way, when you guys do need help, I can just go click on the link, and then boom, I'm like right in there with you. So yeah, just have your Google Hangout link, then you guys can work that way, and then I'll be on call, and then I'll just jump into your little Hangout and help you guys out when you need it. Right? So,
All right, sounds good.
yeah, data structures too. I have to tweak something real quick in the README, but then I will have that posted in the next 5 minutes. So, all right.
Cool.
All right. Good work, guys.